runtime of learning is also a very important concept for learning theory. So computational complexity is very important because when we design an algorithm require a lot of computations, although the algorithm can have very nice performance, to train using the algorithm, to train a model using the algorithm, we may need to spend our entire lifetime. If the algorithm requires billions operations to finish the process, we need a huge, very, very expensive computing machine. And even with such a huge computing power, the algorithm require millions or billions years. So we have to design efficient algorithm, and efficient algorithm means although we increase the number of data points, if we strict our performance constraints, which means we want to more smaller epsilon and smaller delta, our algorithm can guide our model to satisfy the constraint with some feasible amount of computations. So in running theory, there are two important constraints. One is sample complexity and one is computational complexity. So the sample complexity is what we have discussed until now. How many data samples to train our model so that the model can have epsilon accuracy with confidence level of minus delta. This video clip I will explain computational complexity, which indicate the required number of computation operations, like a plus and product, something like that, to finish the learning process. Sometimes we have to think memory constraint as well, especially for streaming setting. For instance, if we implement our sensor device to monitoring our factory, let's say, then every sensor will make some data every time slot, and the generated data will be sent to some central cloud machine. Of course, when we collect more data, we can more easily find hidden patterns, and from the hidden pattern, we can make more precise decision. But the problem is we have limited storage space and we have limited physical memory. So one very naive approach is just remove all the data if we don't have enough empty space to store the new incoming data. That is one possible strategy. And also recently people also think about how to compress the incoming data so that the compressed data can keep very important message and erasing relatively very unrelated data point or some messages, some information. Okay, so memory constraint also very interesting topic for learning theory, especially for streaming setting. But today we more focus on computational complexity, how much computations we need to finish our training. So how to measure the computational complexity? Well, the most direct idea is runtime. We can check the physical time with like a stopwatch. So we can use stopwatch from the start of the training to the end of the training, and how much time we have to spend finish the training. That is computational complexity measure. But the problem of such a real physical runtime is the actual runtime of algorithm depend on the specific machine. So if you use supercomputer, then maybe we need a very short time. But if you use very old computing machine, then it requires huge time. And also some source code can optimize to some specific machine. Um, so it is very difficult to fairly compare all the algorithm in single machine, because some source codes can be designed to operate very well with the specific machine, but some algorithm there is no such optimization process, source code optimization process. So it requires more time than usual case. Right. So this class and in our textbook, people usually think asymptotic runtime. So what is the asymptotic runtime? It is the computational complexity of the algorithm as we increase some specific parameter like a number of training data point or the target performance like 1 over epsilon and 1 over delta. Usually the required training time increase as 1 over epsilon increase or 1 over delta increase or the sample size n increase. So we want to find the runtime growth speed according to such parameter n and 1 over delta and 1 over epsilon. That is called an asymptotic runtime analysis. Right. So for instance, the computational complexity of the merge sort is n log n. Merge sort is very simple sorting algorithm when we have like a data point 7, 3, 5, 6, 1, 9, 8, for instance. And if you want to sort such numbers from largest one to smallest one, then the first step is compare pairwise and sorting. So that's 7, 3, 6, 5, 9, 1, 8. This is one block, this is one block, this is one block, this is one block. And then compare this pair, compare this and this, 7 first. Compare this and this, 6. Compare this and this, 5, 3. Compare this and this, 9, 8, 1. So this is one block, this is one block. So compare them from the beginning. So 9 first, 8, 7, 6, 5, 3, 1. So number of rounds we need to learn is roughly log n when n is the number of entries. And each round we require roughly n number of comparisons. So the total computational complexity sorting from the largest one to the smallest one is n log n. So this is called asymptotic runtime, and here we use big O notation. So I will briefly explain what is the big O notation. So when we use fn equal to big O gn, this implies fn over gn is bounded by some constant, so which it does not grow to infinity as n go to infinity. Then we say the order of fn is at most the order of gn, and we use this notation. Big omega notation is opposite direction, opposite meaning. So when we compute fn over gn and when we make n go to infinity, then this value is low bounded by some constant, so which does not go to 0 as n go to infinity, and we say that the order of Fn is at least the order of Gn. Okay. Fn equal to big zeta Gn implies order of Fn and order of Gn are the same. So when Fn big O Gn and Fn big omega n o, sorry, this is Gn. So when Fn equal to big omega Gn satisfied, then we say Fn is equal to big zeta Gn. Small o and small omega imply extreme case of big O and big omega case, which means the Fn and Gn limitation go to 0. So which is not only upper bounded by some constant but also converts to 0. Extremely go to some value less than infinity, and that is converts to 0 case, and we say that the order of Fn is less than the order of Gn. Big omega is the other side. Fn over Gn go to infinity as n go to infinity. Okay, so big O and big omega implies Fn order is less than or equal to the order of Gn. Fn order is bigger than or equal to the order of Gn, and small o and small omega remove the equality in the order comparison. And this sign also implies the extreme case of the zeta. So when we have Fn over Gn convert to 1, then we say the asymptotic behavior of Fn and Gn are the same, and we use this notation.